All right, so let's try these out. So we're going to look at the shear force and bending moment for these two sections. Again, I'm going to shortcut this process a little bit and tell you that the reaction over here is W naught L, basically the area under this curve, and that the moment is W naught L squared over 2. And you can, bless you, you can, bless you again. Three times the charm, right?
It's always 3.
So in a normal problem, you'd have to draw a free body diagram and get those. I'm sure you could do that. I just want to get right to the topic today, so I'll shortcut that a little bit. So what kind of shear force is this we're starting with? Positive or negative?
Positive.
Positive. And that will be a positive value of W naught L. And what's the shear force on this free end? I don't see an applied load, so it's going to probably be 0. So again, I know that the change in shear between 2 points is the area under the load curve. So what is the area under this load curve? It's a rectangle, base times height, so that's W naught L. And is that positive or negative area? What kind of load is that? Negative. So it would be a negative area. So I'm going to start at W naught L, and I'm going to add to it negative W naught L, and what do you know? I get 0. So I got my endpoints matched up. Now what's the slope? Well, I know the slope of my shear diagram, given by the derivative, is equal to the value of the load everywhere. And what is the value of the load? Well, it's constant, so I got a constant slope. It's equal to W naught, and is it positive or negative? Negative. So here's a negative slope. So again, if I looked at this, it would be 1 to negative W naught. So there's the change in my shear. All right, so we've used these relationships to get shear, and we've constructed our shear diagram. Let's now use the shear diagram to construct our moment diagram. So what do we know about moment? What kind of moment is this up here in the reaction? Negative. So we're going to start off at negative W naught L squared over 2. And what about the free end? What's the moment at the free end? 0. There's not an applied moment there. It's free. So there should be no moment at the end. So again, I know where I'm going to start. I know where I'm going to end. Let's see if that works. Well, our relationships say that the change in moment between any 2 points is the equivalent area under the shear diagram. What is the area under my shear diagram? Well, it's a triangle. It should be 1/2 base L times height W naught L. And that's W naught L squared over 2. And that's a positive area. So if I start off at negative W naught L squared over 2 and add positive W naught L squared over 2, I get 0. Super cool. Now, what is the shape of the moment diagram? Well, I know the slope of the moment diagram is equal to the shear. Those are my relationships I've been using. So let's start at the left side. So the slope of my moment diagram should be equal to the value of the shear. What is the value of the shear at 0? It is positive W naught L. So I'll kind of sketch in a positive slope, and I'll even indicate that that's a slope of W naught over L. And it gets smaller and smaller and smaller until at the free end it is 0. So here's 0 slope. So all I have to do is kind of connect those slopes with the curve. And there's my approximation for the moment diagram. So what's the maximum moment in this beam? It looks like it's negative W naught L squared over 2 that occurs at the fixed connection. So this started off as a line with no slope. Now it's got a slope. And now this should be what? Parabolic. Second order. So far, so good? All right, let's try this guy. Let's see. If I do this right, I think the reaction shear is up, and it's going to be W naught L over 2. Basically the area of this curve. It's a triangle 1/2 base times height. 1/2 base times height. And then the moment will be in this direction, and it'll be W naught L squared over 3. You can figure that out if I gave you enough time. It's okay. I think that's right. This is what kind of shear? Positive or negative? Positive. So we're going to start off at a positive shear of W naught L over 2. What's the shear at the free end? There's not a point load, so it better be 0. The change in shear between these 2 points should be the area of the load curve. Is it? What's the area of my load curve? Well, it's triangular. So 1/2 base times height. And that's positive or negative area?
Negative.
It's negative because the load is negative. So it'll be negative W naught L over 2. So if you start with a positive W naught over 2 and you add that negative value to it, you do get the 0. So that's good. What's the shape of the shear diagram? What's given by the load? So starting here at the left edge, we go up. What's the value of the load? 0. So I should start off at 0 slope. And the value of the load gets larger and larger and larger. Its max here at the end of W naught. Is that positive or negative? Negative. So I should have a negative slope here. And all I have to do now is kind of sketch in the shape. It looks something like that. So there's the value of my shear. And here's where our problem gets a little tricky. I want to do my moment diagram. Okay. Do I know the starting moment? Yeah. W naught L squared over 3. Is that positive bending moment or negative bending moment? Negative. We start off at negative W naught L squared over 3. Oops, my 3 got a little wacky. What's the bending moment at the free end here? 0. Now, according to my relationships, the change in moment, this change needs to be the area of the diagram. Oh, whoa. And you guys know the area of a parabolic section off the top of your head? No. I wouldn't expect you to. I do happen to know that the area of a parabolic section is 2/3 base times height. And if you take 2/3 of that, you will get a positive area that's equal to this, and it will bring you home. However, I don't expect you to know that. And it's a special case, too, because it's truly a parabolic section. It has a 0 slope section. If I just pulled off a chunk of a parabola out there in space and said, what's the area underneath that? You got no way of doing that with just geometry. Very easy if you have the equation for shear and you integrate the equation. You can do that. So this is one of the disadvantages of drawing shear force and bending moment with graphical technique is when you have linear varying loads, it gets a little tricky to start finding those areas and doing this from a geometric standpoint. However, I could easily write this as an equation and integrate this equation to get this equation, and then integrate this equation to get that equation, and graph it. So it's not an unsolvable problem, but this shortcut graphical technique doesn't work very good anymore. So it works great for point loads and uniform loads of all kinds of descriptions, and occasionally for ones that have triangular loads where one side is 0, it works out nice. Trapezoidal loads, oh, that drive you crazy. But you could integrate them, and it would be fine. So again, it's not an unsolvable problem, but this shortcut method. As you see, when I did this, do you see any calculations at all here? It's just, I see this, I know my relationships, I get this. I get this, I know my relationships, I get that. I'm done. And the calculations are just areas of rectangles and triangles and adding and subtracting. So I don't even need a calculator sometimes. So that's the great part about it. You got to remember, this was developed in 1860. There were no calculators. There were just people like you sitting at a desk with pencil and paper. And your German boss was yelling at you to hurry up. I don't know how to say hurry up in German. You might know how to say hurry up in German? Schnell. That's, mach schnell. Hurry up.
Yeah, mach schnell.
I remember that from old war movies. Mach schnell. So I'll yell at you during the test. Mach schnell!
Please no.
I'll do it in my head and smile. I won't do it out loud.
That's fun.
And you like that better?
Yeah, I can live with that.
So at this point, we can do the problem, but I would expect you not to try to solve this problem with this technique. But I'll finish it up. So I know this area is true, so that worked out. Now the slope of my moment diagram is equal to the shear. And how's the shear going to work? Well, it's going to start off at a big positive value, and it's going to go to 0. So I can kind of sketch in that shape. And this would be a cubic shape. But again, you can see the cool thing about this is I still can find my maximum value. I still know the maximum shear is, moment is here. I know it's negative. If you just had an equation, you'd have to examine that equation and see where the maximum value was. Okay,